Yep, looks good. All right. So getting right into it, I sort of touched on it, but the title of this is going to be Fine-Tuning Multilingual Large Language Models for Translation of Low-Resource East African Languages. And my name is Bronson Bakunga, as I have previously introduced myself. And my supervisor is Associate Professor Dr. Siti Zaiton. I currently study at University Technology Malaysia, and I'm obviously at the Faculty of Computing. So maybe we could go to the next slide and we could get started to understand the problem. So the presentation overview is pretty much going to be standard. We're going to have an introduction. We're going to see some of the methodology, and then we're going to see some of the results. I do have to apologize for the slides in general because they're put together a bit fast. Some of the results were gotten just recently, actually. We can move to the next slide. Okay, so since the focus is on East Africa, and this is pretty much where I have at least a knowledge of the languages that exist within this particular region. That doesn't mean that this research does not spread across the rest of Africa. It's just that the languages that are going to be mentioned here are just the ones that I have some information about. So we can see that there are different language families. And this is sort of a problem that I believe African countries have the most, because we have so many languages. So for example, you can see that within this very same region of East Africa, we have Bantu languages. We also have Nilotic languages. We also have a few other languages. But the languages themselves are a bit similar in the way they're formed, of course, because these are families, as we said. So for example, the Bantu language, which is sort of like the biggest one in the region, it has pretty much tonal variations. It also has complex morphological systems. But more importantly is that within this very region, there's 438 living languages. And we put the word livings because some of them might have gone extinct simply because we don't have ways to preserve them. And there's 250 languages in the Bantu group. There's 80 languages in the Nilotics group, 60 languages. So I think you get the depth of the problem. There's so many languages that exist within just a small space, and there's not so many systems out there that address the needs for all these different languages. So we have to do something about it. And why do we have to do something about this? Is because, this is the way we transmit our culture. Language is the way we transmit culture. And so there's also things like traditional knowledge preservation, right? There's so much knowledge that ideally would be passed on using things like oral translation, oral tradition. And that has sort of died down simply because not too many people, with the way things are going, speak some of these languages because of modernization and the uptake of English in some of these areas, specifically in East Africa, I would say. And then finally, intergenerational communication. Again, with the modernization that has come, it comes that some of the more advanced aspects of a language perhaps might be put away over time for the simpler ways of speaking languages. If we can move to the next slide. So I've sort of touched on the issue, but it becomes even more interesting when we start to now really take a hold of how do we solve the issue. If we're going to solve the issue of translation, I believe we should make it in such a way that it is practical. And so in most natural language processing solutions, things like code mixing, and what code mixing is literally if we get one language and then we mix it with another language, so within the same sentence or within the same word. And when things like this start to happen in our daily lives, it also affects the translations that we're going to get from these different systems. So for example, a system that has been trained purely from, let's say, a language like Uganda, which is going to be the focus of this particular research, into something like English, is given a text that has been code mixed. In multiple cases, it always gets it wrong. So like I mentioned, there's access barriers, which is the limited digital content in these particular local languages. That's also a very big issue. So as much as we are mentioning that okay, we have an issue about low resource languages. There's also an even smaller subset of that problem, which is that we don't even have that much code mixed data that exists, or it does exist in places like Twitter, but it's hard to get a hold of. And then we have lack of limited language technology support, and that's currently what we're trying to solve. And so if we're going to look at one example of, for example, Uganda, it's very interesting because you can see from the example shown on the right-hand side that if I wanted to have code mixing in Uganda, and this happens very frequently actually, if you look at Uganda social media or Uganda social media in general, I've given you some examples from X that I pulled today. And you can see that people will take a prefix. A prefix in Uganda might, for example, change the tense of a word, and also the suffix will also change the tense in this particular case. So we are adding the Luganda prefix and suffix to the English root word of saving, and we are creating basically a new word out of thin air. But of course, this could also be the same case that I could just have a Luganda word, could have an English word. And so what happens is you have essentially code mixed, and there's so many challenges when it comes to these systems. For example, if you put the that very sentence, the one which you can see in the first screenshot, into Google Translate, or if you put it into ChatGPT, or if you put it into any other system, for example, Sunbird AI also has their own translation for this particular Luganda problem, you are going to actually get completely different results from what would be expected. And so what's the problem with that, you might ask? It's that if we don't have that correct, then even other things such as sentiment analysis and so many other things such as having chatbot systems becomes almost impractical because they do not have an understanding of practical day-to-day usage of these particular languages. Kata, your screen kind of went off. Stephen. Okay, good. Okay, so I've kind of shown you the issue, but why is this problem not being solved? I've kind of touched on the issue. It's that in the actual in actual texts, in actual different data sets that we have, we do not have code mix data that is added in from the get-go. So all these systems that you're seeing that are for translation don't have any sort of code mixing that's given to them from the get-go. And this is something that is highlighted as a challenge. So maybe we can move to the next slide. You can see this is some of the different systems. So I'm showing you the exact same word. You've already seen it on the previous slide, so you know that it should be the word to save. But because of the fact that it is code mixed, and many of these different translation systems do not have the ability to pick up on that, they will either give you the exact same word, simply cut off, or even assume that it is a different word, or even give you the wrong form. So in other words, if I was trying to convey the message to save money, in the right corner, the right lower corner, you see that when we take this to a solution by Facebook called No Language Left Behind, which has over 200 languages inside of it, Uganda being one of them, it tells you that the same word, okseving asente, really means waste of money. So we can't use this practically in our day-to-day chat systems. We can't use this in our sentiment analysis systems because it's not able to pick up on things that ideally we use now practically almost on a day-to-day basis. Can we go to the next slide, please? So what are some of the research objectives? Well, one, we need to investigate the current state of the code mixed language machine translations for low resource East African languages. We've sort of alluded to it. We're going to fine tune some models, particularly the open source ones, which is Llama and Gemma, to improve the code mixed language translation. And then we're going to validate that using existing metrics such as BLUE and CHRF++. And so in those three, we sort of encapsulated the goals, the focus, and then the technical objectives as well. We can move to the next slide. So what's our methodology and how are we going to go about this? Because we've sort of understood now that the problem is that we don't have enough of this data that exists within the wild for us to be able to incorporate it into our system from the get-go. So we need to solve that as that's sort of the major cornerstone problem to this entire thing. So the first thing is that we're going to actually collect data, and we're going to collect both clean data in terms of we need an actual translation data set that is going to be able to map English to Luganda or Luganda to English. And then we also need to collect data sets from Twitter, from all these other social media platforms that actually do show instances of code mixing. So with that, once we collect that data in the first place, we then go ahead to do synthetic data generation. And so the good thing is that by the time when this research was being done, the first set of, I would say, open source, truly open source language models started coming around, and that's the llama models. So we were able to get the llama 405B model via an API, and we're able to feed it the code mixed instances using some few short examples. So for example, we'd get like, let's say 5 instances, and then it's able to understand within that context that, okay, this is how a code mix sentence looks like, and then we can be able to generate more data from that. So we generate 100 at a time, and then we manually evaluate them to make sure that, one, the code mixing that is actually generated is actually used in normal day-to-day settings. So for example, some sentences might be code mixed sentences, but they don't actually appear in normal day-to-day usage, and that might not make them useful. But more importantly, we only focus on word-based code mixing. So the only thing that we're trying to do is that we're trying to get words. So for example, I am going, and then to the market, we would ideally put to the market in Luganda, or at least one or more of those words. So N words in Luganda to make that sentence code mixed. So can you please share the presentation slides? Yes, I think they'll be shared after this. So the next part, after doing all that, we've been able to actually generate that synthetic data. We've also been able to do that quality control on the data to make sure that these code mix instances actually exist. We then go to the part where we're talking about now what models do we use. And for this particular thing, we want to use open source models because ideally the end product should be open source. So we go for the models that exist, which is the Llama 3.18b model, the Llama 3.2 1b model, and also the Gemma 2.2b model. So after we've selected our open source models that we're going to choose, and of course these are different parameters to make sure that we can fully understand how the translation behaves across models of different parameters. So now we're going to go to the fine-tuning part. And fine-tuning is really just making a model, adapting a model to your specific task. So out of the box, when you get these models, they only do text completion. In other words, if I give it a word, or if I start a sentence, it will continue the model. It will continue the sentence, sorry. And so what we're going to do is that we're going to get those models which already have some sort of pre-training to them. They already have some sort of some understanding, a very small understanding of our languages, in this particular case, Luganda. We're going to give them more data that actually shows how exactly we translate from Luganda to English. And so with that, the type of fine-tuning that we're going to do is actually QLoRa. In this particular case, what we're doing is that we're making sure that we are not loading the whole model, but we're loading a model which has been changed in terms of the precision of the weight. So in this particular case, after we use that, and this is all to make sure that it's efficient and we're cost saving, to make sure that at the end of the day, you can reproduce this in a cost efficient way. And then finally, we're going to iterate through some different parameter sets. So for example, these are things, for example, like the rank and also the alpha. And why exactly we do that is because we also want to see if there's any effects on that. So ideally, this is to what extent does the LoRa adapters that are going to be made actually influence the output of the model. So once we have those parameter sets and we've chosen them, and the reason as to why we've chosen those particular sets is because we wanted to expand on previous data that actually showed, on previous research, that actually showed that it is possible for you to do some instruction tuning, but they did not specify the range of the parameter sets that they used. They only used a rank of 8. And so that is as far as they went. So we want to also build up on that. So in terms of the models themselves, I sort of told you about the base model, but we also try with instruct models. So these are models that already have the assistant functionality with them. So the next thing is that we're going to do inference, and we're going to test with different settings, such as using a temperature setting, or at different settings. And we're also going to test with chain of thought, which is something that came up in the last few months, whereby we're trying to see, when you give these models more time to think through a solution, do they actually come up with better translations, and does that apply to translations in our particular case? Finally, we're going to evaluate using both the blue metric and the CHRF metric, plus the CHRF plus plus metric. And also, we are going to see that there might be some shortcomings there. And so we also introduce LLM as a judge. And finally, we're going to deploy this where we have some quantized models, and we're going to have that you can actually use that into a web UI. So that is the whole methodology. We can go to now break down some individual parts. Maybe we can go to the next slide. Okay, so now we talk about the data sets. So we had a lot of data that was collected, and this had to do with data that was both in Uganda and data that was in, translated. And so we went ahead and then we found public data sets, and there was one which is particularly helpful from the Sunbird AI team, and that's called the SALT dataset. We also had some synthetic data, kind of like how we have touched on, and then community contributions. So these were different things from, trying to reach out to different people, and they actually gave us their suggestions. So quality control, all of these things were done manually, because of the fact that code mixing is not as straightforward as and it's not really understood by the large language models. We had to do this manually for all the 1,000 sets, except the SALT dataset was already sorted. So we didn't really need to do too much on that front. And then finally, the dataset that we came up with has 21,066 instances. 20,000 of those are, of course, Luganda to English translation pairs, which have already been sorted out in the SALT dataset. And those 1,000 are the ones which have been synthetically generated with just sentence-based code mixing. We could go to the next slide. And so I had already mentioned about the synthetic data generation, but this sort of explains it more in detail, and how exactly we did it. So all the prompts and everything that we actually used to be able to do this will actually be included, hopefully within a more detailed paper that would actually come out very soon. It's just being all of this is being put together as we finish. And so there's a quality assurance mechanism. One being that there's some automated filtering. So for example, there are sometimes when the model will just give you back a very long string of text, or it would just give you either fully Luganda or fully English. In that particular case, obviously that would be removed, and then the actual code mixed sentences would be the ones that would be reviewed. Yeah, we could go to the next slide. So let's first establish what some baselines look like. So what we did is that to be able to evaluate this, how do you evaluate something like code mixing? And that's the question that we had to ask ourselves. And so the thing is, we have to generate more synthetic data. So we already generated 1,066 examples of synthetic data. We're now going ahead and we're going to generate 200 separate examples that have not been shown to the models at any one point. So we're going to have 200 examples on just sentence basis, showing the sentence-based code mixing, and then we're going to have 200 examples on word-based code mixing. And from the baselines of existing commercial systems, I would say that GPT-4o is the best right now when it comes to this particular metric. So it shows you that it has a BLEU score of 45, followed by GPT-4, and then Google Translate comes in, and then Sunbird AI, which actually has a notebook published on how you can go about and fine-tune the Facebook no language left behind model that they use. they come in at 33.51. So you can see that the gap between the top and the bottom is quite large. And so we're trying to close that gap to GPT-4. And so some of our results, as we're going to see later on, is that on the word level, we were able to achieve 61.5%. And we're also going to see that, on an LLM as a judge basis, it's 36%. That's also going to be explained in detail, but this is just to give you like a high level overview of everything. And so if we move to the next slide, this is what we got for the sentence level performance, and this is LLM as a judge. So what we basically did is that these models are very good at doing comparison. And so the good thing is that if you're doing a sentence, it's either correct or it's either wrong. So what we do is that we get all of these models, we give them 200 sentences. Those 200 sentences have code mix data, and then we tell them, okay, go ahead and then translate. So when they translate that data, since it's in English now, it's very easy to do a comparison with the actual output that is supposed to be in English. So we do that for all the different models that we have. And you can see that, of course, GPT-4o still comes out on top. Sunbird AI also comes in second place with 68% on that particular benchmark. Google comes out with 68.5. Google Translate. GPT-4 comes with 62.5. And then I'm sort of alluding to the next part of the research where we had to do some investigations. But for now, I will just draw your attention to rank number 7, which is the models that we fine-tuned, which is Llama 8B 128 Instruct. And so you can see that all of them pretty much fall within the range of 33 to 37%. So this is after us training the models for varied periods of time. The 8B models were trained over 100 steps. The smaller models, such as the 2B models, were trained for 50K steps. And this was really just to prevent overfitting. But at the same time, we also have those particular two models, number 5 and number 6, these are models that came about us asking ourselves some questions. So for example, when you look at the range of results for the Gemma 2B and then finally the Llama 8B models, you'd expect that the bigger model would actually be giving you better results in terms of translation, but they're actually really close. So the question became what is really stopping these models from achieving higher scores? And so it became apparent that the fact that you don't have enough pre-training data for Uganda inside of that model to begin with is going to ultimately keep these models at the same level. And so with some experimentation, number 5 and number 6 are us extending the pre-training phase for that particular model, for any particular model. In this particular case, number 5 and number 6 were extended the pre-training of the Gemma 2B model, and we were able to achieve a sentence level accuracy of 51% and 41%, respectively. These need to be leveled a bit better, but in the next slide, I think we shall be able to delve deeper into some of these things. Okay, so we can see that for the sentence level score, I had shown you the side which uses LLM as a judge. And why do we use LLM as a judge? It's because when you actually look at the different translations that are given, so for example, by all of these different models that were fine-tuned, as much as the metrics are telling you that they seem close, some models seemed to outperform the others, even on just a sentence basis. So you could read one sentence and it sounds better than the other one. And so for that, we brought in the LLM as a judge aspect to make sure that it really is like we're just making sure that these metrics that have been given to us are more concrete. And so we can see that all of them are pretty much hovering within the same range, even though they're two completely different sizes. One is 2B and one is an 8B model. Can move to the next slide. But things start to change when we go to the word level, and we're trying to now to look at, so for example, I showed you the word oku saving, which is basically oku. Saving is the English root word, and then is the last word, is the last suffix in that particular case for the Luganda language, and ideally that would mean to save. So we get 200 examples of those, and then we test these models on that. So when we test the models using that, and then we do the different metrics, we can see that actually it shows us that it's not, it's okay, well, the CHRF score does show it a bit better because it's showing you the different, the character engrams, as opposed to the blue score, which is showing you the word engrams. And so because these models are not giving you a one-for-one response about, or a one-for-one translation about these particular words, it becomes that we need to understand the context. And that's the reason as why we introduced the LLM as a judge. So moving away from these scores and then introducing the LLM as a judge aspect, we could move to the next slide. We now get to see a different picture. So whereas on the sentence level, some of these models were down, when we take it to the word side and we give, so we bring the judge, and this judge in this particular case is GPT 4.0, but they were also validated against a different model, which is Claude. And so when we use those particular judges, and then we give them the output of, for example, each word, so we can say that this is the output of the 200 words for example, the first model, which is the Llama 8B64 instruct. And then we give it the correct outputs of those words that were generated. And then we tell it, so you have been given both words. Please assign a score of 1 if it gives you the correct tense, and it also gives you the correct context behind the word. So we're not behind getting a direct translation. We're behind the language model understanding the context, because in low resource languages, it's more important to have the context than it is to have the direct translation. So we do that, and then we give you a 1. But in the case where you only understand the context and you don't give us the correct tense, we'll give you 5. So this is a strict marking, I would say. And then the next phase, we're going to look at the relaxed marking, where we simply look at the context. So in this particular case where we do the strict marking, you can see that our model actually scores the best, and it shows you it has a 61% score of getting those particular words. So it will be able to give you the tense 110 times out of 200, and then it will also be able to understand the context of the word in some particular cases. But you can see that after that, the closest that we get is in terms of the Gemma 2B model, and then the Llama 8B128 model. So really, the models that were fine-tuned for this particular task are going to outperform many of even the bigger models, which was a bit interesting. But once we move on to making it less strict and less about the tense, and we're just focusing on the context, we can check the next slide. We can see that GPT-4o, Google Translate, and GPT-4 now come back to the top, simply because of the fact that now we're giving an equal grading for you having just understood the context. And then they have GPT-4o has an 89% score. Google Translate has a 86% score. GPT-4 has a 79% score. And then right below that, we have one of our models, which is the Llama 8B128 Instruct, coming in at 76%. So this is an interesting gap because it's only 3% away from GPT-4, which is quite good. And especially if you consider the fact that there's a 2 billion parameter model, which comes in at 5th place with being able to achieve 70%, only 6% away from the fourth entry. So this is it in terms of the word level, which shows you a different picture from the sentence level. So moving on to the next slide. So this is it. All of them are ranked. And so now we're going to start talking about the baselines. So maybe you were asking yourself, what are we even comparing this to? So for example, when we started out, if you can just draw your attention to the ones which have unsloth at the beginning. So those are the last 1, 2, 3, 4, 5 models. That is where the baseline was. That is the models before we fine-tuned them. So you can see that the highest in that particular range is 4%. And that's for the 8 billion parameter model. And so we're able to get it from 4%, and we're able to push it all the way up to 37%. And this is on the sentence level translation. And then, just like I said, and I kind of preempted, we thought ahead and we were like, okay, so what's causing the fact that all of these models are sort of within the same 30 range? And then we went ahead, we got some Uganda text that was existing within a Wikimedia data set. We continued training one of the models, which is the Gemma 2B model, and we're able to achieve a 51% score on sentence-based translation. For an open source model, I think that is quite good because most of the other, I think I would say open weights actually. For an open weights model, that I think that's good because to my knowledge, I don't think there's any other one that exists. So this is a good starting point, I believe. So maybe we could go to the next slide. We also looked at the effects of quantization. So quantization is if I got the model today and I wanted to run it on my computer, and I reduce the precision of the weights, then the question becomes, what sort of performance do I get, and are there any drawbacks? At the same time, we also explored different strategies to make sure that that claim to increase the performance of these actual models. So one thing is that the base model, the one which we have trained, was only able to achieve the BLU score is going to be in the blue bars, and then the green dots are going to show you the CHRF++ score. So you can see that there is a drop off from what was previously shown, but at the same time, when we start adding different strategies, so for example, when we add chain of thought, you can see that the BLEU score goes up as well as the CHRF score goes up for both models. And then we can see that when you add, when you put zero temperature, it sort of varies depending on, I guess, the model, because for the Llama model, it actually just reduces the overall translation quality. In the Gemma model, it sort of did improve it a little bit. And then finally, we can see that when we incorporate both chain of thought, which is actually, when I say chain of thought, it just means I'm telling the model to think its translation through step by step. So I'm literally, the prompt is something to the extent of think through your model through your translation step by step, and then maybe we'll tell it to outline all the keywords that it's going to translate, and then finally give me the final output. So that's what I mean by chain of thought. So when we do that, you can see that there's variable output, but when we put chain of thought and the zero temperature together, we see that there's an overall increase in the particular performance of these particular models. So that might be something to actually consider if we are actually running these on our computers or systems where there is quantization to think about. And also that just shows you that if you want the highest precision if you want the highest output, maybe if you're willing to sacrifice about 1 or 2% in terms of the translation output, you could very well use these and they could function as well. But maybe just to note, when we tried this on the 1 billion parameter model, it completely broke down and it just started giving out completely different things. So there is a bit of caution to use within there, that we haven't evaluated all the edge cases. And some of the times when you give one of these quantized models a particular string of maybe to translate, it might go completely off. We can go to the next slide. And so let's now look into the costs, because if we want this to be efficient and we want this to be reproducible for so many different languages inside of the East African region and beyond to Africa, the question is, how much does this actually cost, right? So for the Llama 8B model, we say the one which has a rank of 64, but really this is also the one for 168 and also the one for actually 128. The cost is around $52 to train this. And you can see that the hardware we're using is not really high end. It's A6000. It's not an H100 or anything like that. But at the same time, we are running multiple models on this A6000 simply because of the fact that we've chosen to use in our training Unsloth AI. And so the optimizations that they provide make it that we're using 70% less VRAM in our trainings. And also the fact that we have about a 2% loss if we're using some of the methods that we're using their framework. So you can see that the Gemma 2B model, you can train this for the one which achieved 51% score on the sentence level. We were able to train this for $10. Oh, sorry, no. That one was actually trained for much less. This was the one which ran for 50K steps, and that was trained for $10 across 3 days. The one which actually went ahead and we continued the pre-training. And when I say continue pre-training, we just trained the head and embedding layers of that particular model to add more information. We only spent, it was about $2. because what happened is we only continued training for 10 epochs, which was less than 2 hours, and then finally we went ahead and we fine-tuned it for less than 3 hours, which is also about was about 3 epochs. So you can see that for us to achieve the 51% on the sentence level, we only spent about $2 to get the model to that particular point. And then for the increased word level understanding, we were able to spend this much. So the goal is, if you spend more time training, the model starts to understand the word-based code mixing. If you train it for such a less time, then it's going to have more sentence-based. It might have more sentence-based understanding, but also we didn't train the other model to make a conclusive remark about that. So we'd ideally need to train it much longer to give a conclusion on that particular end. But it's possible for you to do this on a budget without you having to go ahead and purchase H100s, which most people do use in research like this. So moving to the next slide. And so for the deployment phase, we have sort of mentioned it, but we are going to be able to have 4-bit quantized models that you can actually run on your computer, because you need to remember that 2 billion parameter models are just about 1 GB or 2 GB maximum. So that means that you could actually run this large language model, this Gemma large language model, on your computer, and you could be able to chat with it offline, no need for any internet connection, and it will be able to give you the translations. And then also, well, we're going to have a web UI integration, and I think that should be rolled out quite soon enough once we quantize the models. And then finally, the deployment results, we sort of already alluded to that. So 2 times faster processing, and that's mostly on the inference side because of using Ansloth. So we're able to do a lot more faster simply because of some of the optimizations that we made using their library. So I do encourage that, especially if you are on a budget. Next slide, please. And so now this is where it becomes a bit interesting. So we only used 21,000 rows of data, really, and we were able to achieve word code mixing understanding better than some of the bigger models that exist today. But it was also competitive performance, really. It wasn't that the other models, we were unable to reach them. So 51% compared to the next, which was 60%. We think that that's a good starting point, but we believe that obviously that can be improved, and that model wasn't even trained to the fullness. It was really because of the resource constraints that we had to stop that training. And so we think that if you're going to go ahead and you're going to try something like this, you need to go for quality data. And so you need to spend much more time having you'd rather have 1,000 examples, 1,000 code mixing examples that you have vetted and make sure that they actually fit what you actually fit what you're trying to do, as opposed to having like 10,000 examples which are synthetically generated and you haven't vetted them, or you haven't looked through them. Especially if you're going to use something like large language models to create synthetic data, there are a lot of instances where some of the data sets that were created were completely out of touch with what was expected. And so there's a lot of back and forth that you need to do in the data phase to make sure that it's quality. And that's how we were able to achieve the word scores that we achieved. And so we can see that if you want to take on which particular model would you take in any particular case? So if you want to focus on the word level code mixing, perhaps you could go for the 8B. But for general things, it seems like the 2B is pretty much comparable to the 8B in most cases. And it's 81% less expensive to train. It's also 46% faster in training. And it's also going to be much faster when you're doing inference. So when I was getting the results for the 200 examples, the 2B was way faster than the 8B. And of course, if you're going to be running that on the server somewhere, you're also not spending as much to have huge amounts of RAM. And so some of the interesting things, and one of the interesting things is that as much as we were focusing on just translation, it turned out that the models that were trained had extended capabilities as well. So for example, these models that were trained were able to do tool calling functionality, and they were able to do cross-lingual analysis, as well as code mixing, handling, and cultural awareness. So I tried one of the instruct models the Gemma 2B instruct models, and I asked it about, can you tell me the weather prediction for today? And it went ahead, and I didn't expressly tell it that it should use a tool, but I did give it access to one of the tools, and it went ahead and it used you can see right there, the get current weather from the weather tool. And as much as the Uganda produced is gibberish, which is something that kind of comes out from all of these models, is that when you train them to understand both sides, because of the fact that they didn't have enough Luganda in their pre-training data set, it becomes very hard for them to actually put out coherent Luganda. But you can see that it actually went ahead and it called the tool, and it's trying to give you back some of the information. So if you actually expanded that tool call, you'd see that it got the information for Kampala. And what it's trying to do right now is that it's trying to give you back that information in the Luganda that it pretty much knows. And then the second thing is that you could see that I also asked it about, going to Wikipedia and then telling me about a historical figure in particular in Uganda. And it tried to call the search tool, but then there was an error. But you can see that these artifacts or these particular translation systems, as much as they fall short in the translation aspect that we have been focused on, they still do have uses outside of that particular use case. So for example, even when tested against sentiment analysis, these models could start to do sentiment analysis simply because of the fact that they understand English and they understand what sentiment analysis is. We did not, benchmark that, which that's completely like a place where we could expand on this research. But it just shows you like the instruct models are sort of making their way towards chatbot assistance, which is very good because it makes it that we're leaping from just needing to create translation systems to creating chatbot assistance at the same time as making these translation systems, and they're culturally aware. Because you can see the second example, we kind of mention it, but Kabaka Mwanga, Kabaka means king, and so it was able to capture that context and sort of tell you exactly, give you the translation in that particular case. And this is one of the models that we trained. So we can go to the next slide. So what are the future directions? We need to have way more code mixing data, and we need to also have way more pre-training data, to be honest. If this is going to work, I think pre-training is going to be very important for us to get our languages out there. And FineWeb 2 does have so many of our languages, but it doesn't, those languages are not sorted out yet. So I think that would be an effort that we need to take on. And then multi-dialect support. So right now we've only tested with one language, but ideally we want to roll this out to have 2, 5, 10, or even like 400 languages for the particular region. And that of course brings its own set of challenges. But obviously this is something that we can obviously research and see if we could just get a data set of multiple languages, put it all together, put in code mixed instances for all those different languages. Does it perform as well? That's something that we need to find out. Also faster inference, and how can we make it that these models, whereas yes, we've trained them, how can we make it that maybe they take less size, and we can also be able to deploy them in different places. So data expansion, also touched on that. And then finally, edge device goals. So interestingly enough, I believe if you get the code mixed, the language models that we have pre-trained for particularly Llama, you can actually run the 1B version on your phone if it is quantized. I believe there is a way for you to actually get that fine-tuned model onto your phone. And this just creates a lot of possibilities for you to have offline translation, which might not have been possible in the first case. Even you just having these models just makes it that you can have offline translation or offline chatbot capabilities for your different languages, which were not possible, just a few moments ago. Real-time translation, so obviously that's a goal, and making it that these models are able to translate so many different things, so we could be able to then go ahead and transcribe so many of the different videos or so many of the different audios that we have, and that means that we can create more data, which we can then feed into these systems and create a feedback loop. And As of right now, all of these models are actually available on my Hugging Face. So they might not be well documented in terms of the README files, and I apologize for that. It's just that there's been so much that's had to happen, and so I will make an effort to clean those up and make sure that we also have the notebooks and also have the different data sets that have been mentioned to that particular regard. And all of this is going to be put out there in case you want to reproduce this. Sorry about that. I'm just going to put it in the chat in case you are interested to check that out. And so, yeah, you can check out these. You can actually just play around with them. I believe the instructor versions will be much better than the base versions because they already have some understanding of instruction following. But yeah, that's pretty much it in terms of the future directions. And lastly, we can go to the next slide. So we just want to highlight some of the key achievements that we have for open source models and open weights models. And I believe, this is like the first of their kind. Being able to achieve a word level code mix sentence translation of 61% was really great. And then also having a sentence level of 51%. I hope I didn't mix the two up. Sentence level of 51% with a Gemma 2B model, the one which is pre-trained, continued the pre-training is also great. And the different blue scores and having to use less VRAM to train these models is obviously very interesting. And so the research impact, we believe that being able to achieve this with 21,000 examples makes it that we can effectively do this for the vast majority of the languages. So we don't need huge data sets to start to actually, do translation systems like these. We can use just 21,000 examples, the 1,000 being code mixed examples or even more, and we can start to do some sort of, efficient translation systems. And so we also have the 2 billion parameter models, these very small models, ideally, that can run on your PC, on your phone, that you can actually use, and they can match somewhat the performance of an 8B model. Production-ready deployment is that when we have the quantized versions ready, you could check these out and see how they perform for maybe even Uganda retrieval augmented generation. Who knows? The sky's the limit because we haven't tested the full capabilities of the models. We have mostly been focused on the translation side of things. And so this research is mostly tailored towards low resource languages, and we're trying to make it that Africa does not stay behind in this AI age, and we're able to bring more systems for our actual local people forward, and then we're able to create not just translation systems, but chatbots, things like sentiment analysis tools, all stemming from this one point of research, which is what we're trying to do here. So I hope you enjoyed it. On the next slide, I do have some references to some of the work. I have to, oh no, maybe it was an issue with uploading. I have to give credit, of course, to the Sunbird AI team. They do publish a lot of their research in terms of the notebooks and a lot of the different things that we are pretty much building on here have already been built on by different people. So Facebook also put out a great research paper called No Language Left Behind that is pretty much also fed into this. And there's one other paper that also is called Lermatuk that talks more about trying to do this sort of thing in detail. So we're really grateful for the opportunity to actually present this, and I hope you guys enjoyed it.
Yes, thank you, Bronson. We are going to give, hopefully the call doesn't end. We're going to give a few minutes for a few questions, like 5 minutes. And those who have questions would ask Bronson, but thank you. The session was good, and that this is why we want to host sessions to the African community. So the floor is open to anyone who has questions now.
Yeah. So I'm going to just first finish the ones in the chat, and then I'm going to pick the hands which are up. So one asks, have you published an article about your work? If so, can we have the link to it? So not yet. I'm actually still ironing out a few rough edges, kind of like why I also the Hugging Face is a bit disorganized. So I apologize for that. But very soon that all should be in place, and once that happens, I should probably be able to put it in the Cohere group in Africa. All right, maybe I can take some questions. I think Rogers had his hand up first, and then I'm going to come to Pius. I hope that's fine.
Yes, Brandon, thank you so much. This was a great insight and a wonderful session. I really enjoyed it. And if we can have actually a friend is the one who shared with me the link because he knows how much I'm always interested in joining such kind of session. And they're also rare and building such kind of capacity in Africa. We lack a lot of useful information like the one you're giving us right now. And I really appreciate what you're doing. So I was just trying to ask whether is it possible to connect with you like on social media and the rest. And
Yeah,
secondly, yeah, yeah, I wanted to also have maybe if possible you can share with us your slide too would be great.
yeah. I think for the slides, we are just going to put them directly in the Africa group. Oh, sorry. So that might be hard. Because some people are not in the Cohere for AI group, I believe. So maybe we could maybe
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 Katoro
Stephen,
would
yeah, maybe Stephen
like
can help.
on LinkedIn, like a link to the page.
Okay, I'm really sorry. Maybe you can just because you're talking of a group, is there like a team group or where I can also join in and be part of this? I don't miss this session always.
Yeah. So I think the best thing is that if you joined externally, please I think the best thing you can do is that you can reach out to any one of us, and then we can help you get started. I think Kato is actually the regional Africa lead, so he can help you just find out what the requirements to join. But you just simply have to put in your request to join, and then the team will go through it. So actually, yeah. So here's the link. I've kind of shared it in the group. So please sign up to that. You can also reach out to me directly on LinkedIn, and we can be able to talk about anything else that you might have. That
Thank you so much. Thank you so much.
All right. Thank you. Pius? Yes, please.
Yeah, hi, Bronson. Yeah, I have two
Hi.
questions. Yeah, so I'm new to LLMs and I was doing a course on democratizing AI with InstructLab. One of the
Yeah.
concepts that they were using to train models on synthetic data was to retrain the model on the old data they had trained it with. So in this context, when you train train this model with code mixing for informal situations like on Twitter threads and such, does it affect translation in formal context?
Yeah, so that's actually something that I'm still investigating, but it seems to be that there is a trade-off. So, but the question also becomes, how much of that was due to the fact that there wasn't enough data to begin with, right? So, it's something that I'm still trying to investigate, and I'm still trying to get the exact scores for example, BLEU from just plain Luganda to English. But from what I could tell, I would also need to test it on the pre-trained model to see if the constraint is not really just the training or the new training. It might actually have to be with the data. So something I'm investigating, but it is interesting. I believe that there might, for now, it just seems like there is a trade-off.
All right. So for my next question, where did you train these models?
So I used Massed Compute. I'm very sorry for not sharing that. There's a platform called Massed Compute, and I happen to have a coupon code which allowed me to get an A6000 for $0.33 dollars per hour, which might be interesting if, for example, if you want to try it out. I think I've tried some of the other systems, so Vast AI, and I believe there are a few others which are usually recommended, and I think 0.33 is about as cheap as you can get it. I'm not too sure about that. But in case you want to try it out, mass compute, and then the code is Marvin Price-Hunt. So I watched it from a YouTube video. But there's so many other platforms. Like I know there's Vast.ai as well for training. And the difference between mass compute and Vast.ai is that Vast.ai you're using someone's computer. So people are literally just giving you their computer for you to try train different models on, so the quality usually varies. That's why sometimes I use mass compute, because you know exactly what you're expecting. It's an A6000, the internet speeds are going to be the same, and so many other things like that. But there's so many platforms. I'm sure there's even RunPod and something like that, but mass compute is the one which I used.
Thank you.
Right, thank you. Yeah, James, please go ahead.
Yeah, so I wanted to ask if the platform you made mention of, they provide the open source models as an API, or you have to load them from Hugging Face?
Yeah, you do have to sort of set them up yourself, but I think we are trying to focus. We're trying to make some content around that, and actually, I'm also making some videos in regards to, how maybe you can set up some of these things. Maybe you could serve them yourself. But these platforms basically just give you, depending on what you have. Actually, let me just check the Docker real quick. They do have some Docker. They do let you pull in a Docker instance. So maybe that could be something that you'd explore. Mass Compute has a provision where you can just put in like the name of the Docker container. So you could be able to find a Docker container online that that's already set up with let's say something like Llama 3.21b, and then you could just pull that in and then see how it works. But I haven't tried it.
Okay. So in your case, how are you able to work with open source models via APIs?
Okay,
Or
so
like
yeah. So okay. So you want to check out a platform called NVIDIA NIM. And if you're a student, I believe they do, if you use your student email, they will give you about 3,000 credits, if I'm not mistaken, which is quite a lot actually. So you'll be able to do different
experiments.
different experiments with that. And so you'll be able to access all of the models that they have. They have Nemotron, they have Llama 405B. And so that's why I was able to like use that. And so you can just experiment with that, especially given the fact that if you're in a university, you can just use those credits, and then after that, I believe after like a month they'll disappear. So you want to use them as quickly as possible as well, because mine sort of disappeared without me using them to the most, but you get a lot of credits.
All right, then. Thank you.
All right.
Okay. I guess let's give a hand clap for Bronson for such a wonderful session. Because
Kato, Stephen,
yes.
are you going to share the recording?
Definitely, I will share it in the.
I look forward to the recording, and thank you, Bronson, for that wonderful discussion. I personally am going to engage you because I really need your support on some things. Yeah, because I've used Sandbird AI APIs to do some RAG applications. So I would really love to read more about your work and see if you can guide me in case I need to upgrade my skill set. Thank you.
All right then. Maybe one last question before we go. I see James has a burning question.
All right, thank you, Bronson. Mine, I was on and off. I don't know if you mentioned it.
Yeah.
But mine was in regards to finding out which one is harder, fine-tuning the LLMs for the 42 languages, or explaining to someone why Google Translate is actually not there. I mean,
Yeah. So I think, it's kind of like the same thing. Not having enough data. And actually, I think
Mm.
Google Translate and all these systems that we're talking about have improved drastically from the time when I started this research. So I started about 1 year ago, like about 16 months ago. And compared to where they were at that point in time when I was testing them, they have improved drastically. So that's also a hard thing because at the point when I was starting out my research, it was a bit grounded with when they weren't so good, but they keep on increasing. So I think this has to do more with how much data they're having. So of course this is a completely different thing when we're talking about Uganda and we're talking about maybe the 41st language in terms of like the amount of data sets that you can get. That makes it completely different. But if we can use synthetic data and we're able to weed it out and we're able to have enough data to actually do some pre-training, I think you could possibly do it. It's just that I think for Google it's a bit tough because how like the question is also at the end of the day, like how many people are using the language, right? So I think that's sort of maybe what they look at. And for us it's about our cultural preservation and things. It's pretty much we're scratching our own itch. We don't have translation systems trying to make them. For Google it's maybe let's get the most spoken and then let's bring them in. Of course, I'm not too sure about that, but that could be one of the reasons as to why. But also getting data for these things is extremely, extremely hard. And I don't think I would have been able to even reach this point if I didn't find the Sunbird AI dataset, because that was pretty much the only clean data set I could find on something like Luganda translation and even Swahili and some of these other languages.
All right. Thanks about it.
All right.
That's
Thanks
about
so
it
much.
for me.
Thank you.
Yeah. Again, let's give a round of applause for Bronson. I will share the slides in the group, and those who are not part of the Cohere community, I put the link there that has forms. You could just apply, and the leads at Cohere will select you to join the community. Grateful for this session. I will share the recording. Bronson, we will always keep talking. There's more work. There's more work coming, and thank you for it. It was a good presentation, and I'm going to pass it to someone, probably at the office of the president of Uganda, to see the work, and hopefully they could help out. Yeah. So thank you so much, and we meet in the next session.
All right. Thank you so much. See you guys.